Yeah, my name is Philippe. I work for ARM in the open source software group. More specifically, I'm part of this new team which used to be robotics, but now we have a bit more focus on the automotive area. So today's presentation is going to be about a new project, which is called the DDS Sec. And the goal is to move all the security implementation, so everything you have seen on the previous presentation, we want to move all that implementation into ARM Trusted Zone, which I'm going to explain what it is. So I'm going to start with some key concepts between DDS and also ARM Trusted Zone. I'm going to probably go quite quickly on the DDS because it was explained already. And then I'm going to talk about the project itself, what's the current state, and how we are trying to implement it. Right, so I imagine that everyone knows about this type of diagram, but it's just for completeness. What we are trying to accomplish here is to protect the communication between the nodes within a DDS domain. So our work is more specific to ROS2 in this case. Again, previous presentation already explained this, but just to give you an idea, the DDS specification is quite actually a lot. There is a lot of specification. There is a collection of specifications. The main ones that have a relationship with the work we are doing is the DDSI or TPS, which talks about the low level, how the frames are packed and how it's transmitted on the wire. Then the DDS high level specification, which gives the information how the data is communicated. And finally, the main specification for us is the DDS Security, and that gives all the details about the model and the plugin interface. So there are a few things that the DDS Security tries to protect. So very quickly going through them, confidentiality, which is about make sure that two nodes can communicate and no one can know what is going under that transmission. Integrity, so you know that what you receive is not corrupted. Authentication, where you can have a node to say who it is, and you can trust that. Authorization, so after you have the nodes, you can say which node is allowed to do what in terms of publishing data or receiving data. Message data and origin, so again, it deals with authentication, so you know where it's coming from, the information that you're receiving. And finally, non-repudiation of data, which means after a node has sent that information, you know that it cannot lie about it. It has sent it. You cannot go back and say it hasn't. So the DDS security specification has quite a nice chapter about the threat model. So they talk about these 4 items, and there are very nice description, diagrams, and how it works. So this is just more for reference if you want to see it into more details. So going down into the implementation layer, there are 5 plugins. That's how it's approached in the specification. For our work, we have been mainly focusing on these 3 ones, which is authentication, the cryptography, and the access control. Though access control, we haven't yet started the implementation on it. Right. Just a few more details. The DDS specification actually gives you, it pinpoints how the communication needs to be, which algorithm needs to be used, but it has some options at some extent, actually. For us, we have been approaching it more or less on these 2 items. So all the asymmetric key cryptography is just used for discovery, authentication, and the creation of the shared secret. And the other information is that the use of ciphers, the HMAC or digital signatures, it acts on a topic level. Again, how it was explained in the previous presentation. Okay, that was the quick overview of the DDS nodes and security. So I'm going through the ARM Trusted Zone. I don't know how many people know about the Trust Zone, ARM Trust Zone. Okay, not that many, which is fine because I got diagrams about it. The one phrase description is that Trust Zone is it's a built-in technology inside the CPU, which pretty much creates 2 virtual environments. and you can have two completely independent software stack running on it. It's quite generic in terms of which are these two software stack, but conceptually, you always consider that one of them is secure and the other one is non-secure. But it's just a concept. It's pretty much just two words executing apart. The main way that is accomplished by the physical address is kind of split. You can say which range of the physical address is attached to one of the two words. And the security and non-security is completely orthogonal in terms of the privileged levels, which I'm going to explain in a minute. Right. So, in terms of trust, security. It's all about who you trust on the system, right? So, it used to be as simple as this diagram. So, you have many reasons to have OS, but one of them is about the isolation. You have multiple applications running on top of the operating system, and you know that between two applications they are not going to clash because the operating system is doing the isolation. So you, in this point of view, you trust on the OS doing that level of isolation. More recently, we have something more like this, where, for example, if you are renting a server on the cloud, you might don't trust to run your application together with another application from a different company, even though you might trust on the OS. So more recently, we have the hypervisor, which does another layer of isolation. So you can have your own OS and your own application, but you still need to trust that the hypervisor is doing the isolation. Now, you could do some security aspects using this topology, but that's where we get to the trust zone. So on ARM CPUs, you have another layer, and so the EL means execution level. It's just a privilege level. And okay, so during the boot sequence, what happens is that you always start, the ARM specification says you always start on the highest level of the execution level. So the EL3 is always secure, where all the other execution levels have secure and non-secure sides. The EL2 is not showing the secure side, but that was added just a few months ago. So there is a EL2 secure now, actually, which ARM just released as an extension to the CPUs. So during the boot sequence, usually you are going to boot into the EL3 mode, and that's considered the secure mode. So you usually are going to have like a ROM into the system. That ROM is going to load the remaining, the further image. So that's going to be, for example, the trusted OS. So it loads, it verifies that it's really a valid image. It has internal keys to make sure it's valid, and it knows that it's the chip vendor that signed that image. And then it can load the trusted applications on top of that. Once it has done that, then it loads the non-secure world, which can be just like Linux or Windows. And they can now coexist in parallel. Every time you want to invoke a service on the trusted application, you need to go all the way down to EL3, so like using system calls, etc. So you keep escalating the exception levels, and you move to the trusted application, you execute what you need to execute, and you go back to where you came from. That's how it gets isolated. So for us, our environment, you have, if you haven't noticed, it's the names that change. So the EL3, we have trusted firmware A, which is a trusted firmware for application CPUs, and we are using the OptOS, which is one of the implementations of trusted OS. It's an open source one. I think I'm running a bit late, actually. So very quickly, the libDDSSec project is trying to move everything from the non-secure side into the secure, all the security operations. And that means all the certificates, management, all the key generation, and all the security operations. The main goal is to just limit the surface attack, and more specifically, we want all the keys to be only in the secure, and there is no way for them to be leaked. So this is a typical implementation of our DDS. We are using FastRTPS as our environment for testing. And usually they use another library like the OpenSSL. And all the certificates, all the configurations are in the non-secure world. Our first proof of concept has been something like this. So we just remove the OpenSSL layer and we create our own API. And there is a backend which then invokes this trusted application. And everything is on the top right side. All the execution happens that TA. That was the initial proof of concept. So now it's becoming a proper library. So it's outside the DDS implementation. And that's how we are trying to do it right now. So just 2 minutes more then. The next step is, we still have problems with this topology where the green arrows going down, they might be very specific to a given implementation. So what we are looking to is to move even the plugins inside this library. So what we can do is just instantiate the plugins itself in the library and just attach to the DDS according to the DDS specification. I'm just going to skip this one. That's the current work. We're trying to move now things from the proof of concept into the pure library. Main challenge, so the latency might be one of the main challenges we are going to face. We are trying to, it's always a trade-off, so that's something we need to make sure it's going to be worth doing. We still have a problem where vulnerability on the non-secure side might allow things to say, to use the secure content, but at least it cannot leak the keys. That's the main idea. Skip the future works. So this is going to be our open source. We are trying to push this to GitHub very soon, as soon as we have it available. It's going to be mainly a BSD project written in C and C++. Final slide, I promise. It's the reason we are doing this is because we are focusing maybe on the automotive area, and as you have seen today, there's quite a lot of automotive projects using DDS and also ROS2. That's it.
Did you have an idea of we won't have time for questions, sorry, but did you have an idea of the time frame in which this will be available?
So yeah, we're still trying to, as soon as possible, but we have the hope that's going to be during this next quarter. Thank you very much.